Okay, so in 14.5, we're going to introduce you to cylindrical and spherical coordinates. Maybe not for the first time, maybe you've seen it before. But we'll hit these, and then in the next section, we'll see how to integrate by converting over to here. So just like you did converting to polar coordinates to make double integrals easy, we'll convert to different coordinate systems in this case. That's something written on my paper. I don't understand what I'm trying to say. So let's just forget about it. So cylindrical coordinates first. Okay. So bear with me as I draw this. So here's a point in space in rectangular coordinates, right? So our normal coordinate system that we're used to. And so all we're going to do in spherical coordinates, so we'll denote this point by x, y, z in rectangular coordinates. In spherical coordinates, it's essentially polar coordinates in 3D. We treat the z's, we just leave the z's as z, and then we treat the x and y as though they were polar coordinates, right? And so your z is still giving you your height, and then we just draw it. So your r is this distance, and then what is theta represent? The angle between the x axis to r, right? So it's this little angle right there is theta. Does that make sense? And again, you can get away with all different values of theta. You can do negative r's that push back into your direction. Once you're in 3D, though, sometimes that's pretty ugly to try to deal with. And so even something as simple as plotting points can be a little bit painful. But let's try it and see how we do. So plot the following polar cylindrical points. Okay? And so I'll just write them down. So 2 pi over 2, 3, 1, 3 pi over 4, negative 2. Here, let me put this one will be kind of weird. 0, 726 pi, and then 5. All right. See how you do with those. So again, I want to plot them in my regular x, y system, but I guess I don't care. You don't need to get the x, y values, just plot them. All right, so this is a negative 2 here. So let's do that first one. 2 pi over 2, 3. So the pi over 2 and 2, just ignore the 3 for a minute and plot that in the xy plane. So where is that? On not the x, the y-axis, right? So your angle is here, so you've got pi over 2, so you're sticking out here, and then you're going to go 2 units over this way, right? And then go straight up 3 units. And again, don't worry about being super precise, but that should be that point. So 2 pi over 2, 3. All right, how about the next one? 3 pi over 4 is where? Yeah, this one's a little bit goofy. So maybe if you have, let's just draw it on its own set of axes. And I'll draw in. So first of all, where's that angle? 3 pi over 4 is, yeah, it's 45 degrees, but this way, right? So, and I'll just draw in a dotted one. So you go out there and then you go out 1 unit out, right? So again, that's your 3 pi over 4. And then what do we do from there? We drop down 2 units, right? So if that's 1 unit, just eyeball it. Again, once you've moved to someplace else, it's not clear. Did you get that? And maybe I'll draw solid lines just to make it clear. Right? We're behind that axis. We come down, right? And then, again, we've gone down. So then that's the point 1. 3 pi over 4, negative 2. This is another situation where drawing something that's perfectly, obvious to someone else is less important than being able to visualize it yourself and know where those points are sitting, right? You really just need to be able to draw it well enough that you know what that means. Okay? And then finally, that last one. Oops. Well, let's just draw it on one of these other ones. So if your radius is 0, where are you? You're at the origin no matter what your angle is, right? So you're just at the origin and then you're going up 5. So it should just be this guy here, right? So that would be the point 0, what did I say, 726 pi. Okay. And just like always, right, there's multiple representations for a point in cylindrical coordinates, because if you add 2 pi, right, you'll wrap right around to the same point. And then like I had said before, if you add pi but make it negative, that'll correspond to the same point, right? You'll go 180 degrees and then backwards. And so just be aware of that. As long as I have this up here, let's just use this. We still have all the same identities that we're used to. They still hold for cylindrical coordinates. The identities from polar coordinates. Right, you're just treating x and y as though they're polar coordinates now. So it's those same identities. What else? I guess tangent of theta is y over x. And then you get the really important identity that z is equal to z. So remember that. You add that one in there as well. Okay, but so these are the coordinates, or the formulas you'd use to move from polar coordinates to rectangular coordinates or vice versa, right? And again, I'll just stress again, treat the z as though it's z, and then shift the x and y into polar. Okay, so let's sketch a few things here. Convert r equals 2 into a formula in rectangular coordinates. And sketch. All right, and then well, let's do that first. Okay, so r equals 2. So to convert to rectangular coordinates, you just want to get these things involved. I suppose most of the time there's more than one way to do it. But the easiest thing is to try to incorporate this, right? X squared plus y squared is r squared. So if r is 2, oops, then r squared is 4. Sometimes it's useful to do r squared is, right, you could have also done r squared was 2 times r, right? There's all kinds of different variants that show up from time to time. But this is the one we want to use here. And so then what's the x or the r squared get replaced with?
X plus
X squared plus y squared equals 4, so what's that? Circle, but we're in 3 dimensions, so not a sphere, a circle in 2 dimensions, right? And then drag up, so it's a cylinder, right? That makes sense? And hence the name cylindrical coordinates, right? So you can really easily write down cylinders in cylindrical coordinates, and that's why they'll be valued. Okay? Let's try another one here. Convert z equals, so this should be easy too, x squared plus y squared to cylindrical coordinates. And sketch. So just going the other direction. And then do the same thing with, let's just, same direction. I'm just going to call that one A and then B. Just a simple sphere. Okay, so let's just go through this. So the conversion is pretty easy. What is it? Z equals just r squared, right? And then we've seen this one a bunch. What is this graph? Z equals x squared, z equals x squared, y squared, right? It's just parabolas in both directions. And so you should get just this bowl shape coming up, right? Something like that. Does that make sense? Show stuff that's behind if you want, but again, the main thing is that you visualize it yourself and you realize what these things represent. Okay, polar coordinate or rectangular coordinate formula for the sphere then is what? Well, just the formula is r squared plus z squared equals 16, and this is what? X squared plus y equals sphere with a radius of 4, right? Again, draw it however you want. Okay. Last thing for cylindrical coordinates. What is this? Okay, I agree, but let's so we will do the conversion to polar coordinates here in a second. To rectangular coordinates, but let's sketch it without any of that. So we just think about what this represents. So our angle is pi over 3. What's that? 60 degrees. Your angle 60 degrees. What's your r? Remember, this was what? X squared plus y squared equal, oh, I didn't even, what was our thing here? I never labeled this one. Oh, this was 2, right? X squared plus y squared equals 4. So this was. So remember, this was just the circle in the xy plane. Since z didn't show up, you just dragged it along, right? So here, theta is pi over 3. R doesn't show up. So you go, yeah, so you go all the distances in R, right? It goes backwards into the board too. I'm just going to draw this piece. And then Z also doesn't show up, so you also take every one of these and go straight up and down, right? So you should get basically that plane that goes out. Does that make sense? So that horizontal plane. Now let's try to come up with an equation for this. Now you could look at what it was, but let's look at our identity. So we had x squared plus y squared was r squared, x was r cosine theta, y was r sine theta. What other ones do we have?
Theta equals to y over x and
Okay.
z equals to
Okay. And actually, let's just stop there. This is the useful one, right? Because you know theta. So if you just plug in pi over 3, that's what theta is always equal to, right? You get this, y over x. What's tangent of pi over 3?
square of 3.
Yeah, sine of, yeah, root 3 over 2 over 1, yeah. So square root of 3 equals,
That's 3, not x.
oops, root of 3, maybe. So y is the square root of 3x. Does that make sense? So there's a rectangular plane for it. And so every once in a while, it'll be useful to take a thing like this and convert it to polar coordinates. So to sort of go backwards. So lines through the origin, you can always come up with a nice formula for them in terms of polar coordinates. Well, I should say planes. Planes parallel to the z-axis through the origin, you can come up with nice equations for them. But I think I'll stop there rather than get into the spherical. So next time, we will talk about spherical coordinates, and then we'll move into integrating in terms of spherical and polar coordinates. All right. Good.